Hello. Hey guys, thank you for attending. My name is Archit. I work at the Qualcomm Innovation Center in Bangalore. And for the last few months, I've been trying to figure out how we can align to upstream. So I'm going to explain a couple of some of the issues that we face. And I'm guessing there would be similar issues that other SoC vendors would also face. And what lies ahead in the future. So this is the rough agenda. I'm going to first start with describing how Ion is used on Qualcomm chips with respect to an Android user space. Then I'm going to run through a couple of changes that we have in the downstream kernel and why can't we get some of the things upstream and what is the plan in general. Then I'm going to quickly cover secure heaps and what are the challenges to use Ion on virtualized platforms. Okay, so a quick recap. These are the existing Ion heap types. Are you guys familiar with Ion to a certain extent? All right. So we still use a lot of the system heap. System config we don't use as much because it's prone to row hammer attacks. Carve out in chunks. Chunk heaps are also, a bit ancient. They were more prevalent on older generation of SoCs, but not anymore. And the DMA type, which is basically CMA heaps, we still do use them. So these are the custom heap types that we add, and anyone that wants to use these heaps has to include this UAPI msmion.h to use these heaps. So it's good that we just have 3 heaps and they're all for like allocating secure buffers. I'll get more into these in the secure heap section, but the main way by which these vary is how access control is implemented on these. So the first one, secure DMA, was used on older generation SoCs, and it implements slave-side access control, where slave is the DDR with the RAM, and the next 2 heaps, the system secure and hypervisor CMA. They implement access control via master side access control, which is basically preventing certain devices like the display or the video or GPU to access the buffer in the first place. I'll discuss these in more detail later on. So I'm going to roughly describe the users of Ion on a Qualcomm/Android chipset. So Gralog is, as we know, it has an Ion backend, and it's further tied up with the Surface Flinger and Stage Fright and so on. So that's probably the primary user of Ion in the Android user space. Then we've got a lot of proprietary and miscellaneous user space libraries and applications. The ones that I've shown is still a small subset. It actually, there are probably a dozen more, which I didn't have space to put in. And the final set of users are in-kernel clients. This sort of kind of shows what each client uses, what heap type each client uses, and the place where it's split into 2 parts basically means that there are some use cases in which it uses, say, a system heap, and there are other use cases in which it uses a secure heap. So in most of the cases, the split is basically to differentiate between secure and non-secure use cases. Any questions until now? No one's curious about the proprietary libraries? Okay. So I've described the users of Ion. Now, how do they allocate it? So Yeah, oh, sorry. Before I continue, this is the first problem that we've encountered. How do we deal with in-kernel clients? The way the discussions are going upstream, the maintainers and most of the guys don't like the idea of spreading kernel API to do allocations within the kernel. But we have a couple of legit reasons to do allocations in kernel. So, for example, the video encoder decoder IP, it allocates a lot of scratch buffers as a part of the decoder encode process, and if the pipeline is a secure pipeline, these scratch buffers also need to be secure. And the only way we can do secure allocations at the moment is to use Ion. And the other reason is that, so there are still a few clients that use system heaps inside the Android kernel, and we could ideally use the standard DMA mapping API and do a DMA alloc coherent, and rely on the DMA mapping framework to back it via the IMMU. But the system heaps just tend to be a bit faster because they have another layer of caching. The Ion maintains a system, a page pool for system heaps, so it just makes things faster. So why shouldn't we use Ion if we can get better performance? So that's the first problem. How do we deal with in-kernel clients? Do we stick to them or do we get rid of them? Okay, so this will describe like how does a user, I'll stick to Userspace for now. How does a user specify which heap to allocate? So the answer is heap IDs, and a heap ID is basically a hard-coded number that represents a heap instance of a given type. And as you can see, this actually contains all the heap instances that MSM chipsets have used since the beginning of Ion. And they vary a lot, and a lot of the heap types are no longer even in use. So the only reason to stick to them is to not break user space. If we want the user space to work with slightly older kernel, we don't want, like with a slightly older chipset, we don't want these old heaps to go away. So a particular platform will not support all these heaps. It will only be a few subset. It will be a small subset of these heaps. Yeah, so a user is supposed to pass this heap ID in the Ion allocation API, the Ion allocation IOCTL, and pass the heap ID or a mask of the heap IDs to do its allocation. So the next step is like, okay, we know how to use and allocate the heaps, but how do we instantiate it on the platform? So I'm not sure if it's entirely clear, but this is a DT binding that we have on the Snapdragon 835 SoC. So it contains a parent Ion node, and inside it there are 6 children, and each of these represents a heap instance. And if you can see, there is a rec field that corresponds to each of them. So these are actually the heap IDs that we described in the UAPI. And these need to be the same, otherwise things just won't work. There are some other parameters depending on the type of the heap. So we also mentioned the heap type, as it's here. And there might be additional parameters, like for example, for CMA-based heaps, we might need to explain what's the range from which you can allocate the CMA heap, and what's the size of the heap. So this sort of brings us to the second problem, which is it's not an agreed on thing to have ion DT bindings. So we need to specifically describe somehow what are the different heap instances we want. So if we can't do DT, then what's the alternate solution? Yeah.
Okay. The point is that it's not that it's not ion. The ion-specific data is not specified in DT. That's what it's supposed to be. The point is that you can specify all the CMA regions as you want, and then just have those become enumerated with the new method. So.
Okay. So I mean, these are going to exist anyway.
Yeah.
So you want to somehow hook that into ion.
Well, yeah, it's already hooked up with the newer work. The way the newer ion ends up working is that ion just enumerates all available CMA regions, okay. And then you use the query mechanism to be able to find out what those heaps actually are. So
okay.
That's
okay.
how it ends up working out.
Okay, so, and I guess system heap and the other ones are, anyway, you don't need to.
Exactly. Yeah. So the system heap just gets created automatically. You select the appropriate tag along with system config heap. So.
Okay. All right. Okay. Okay. So I'm just going to run through a couple of Userspace libraries that give you a rough idea on how does the allocation work. So so this is like a video post-processing library where it's quite straightforward. If the use case is secure, if it's a secure buffer, you kind of allocate from the secure heap, and if it's a non-secure buffer, you just allocate from the system heap. There are some additional flags some semantics that we need for secure heaps, which sort of makes it platform specific, but I mean, we'll discuss that more. So Gralloc is another example, one of the main users. So this function translates the Gralloc usage flags into specific ion heaps, and as you can see, there are a lot of cases. So if it's a protected usage, then you use the secure display heap, and if it's used with the camera, you do something else. And if there are certain Gralloc private flags that I guess make it a Qualcomm specific Gralloc in a way, but you've got corresponding heaps for those guys too. And I mean, I'm not even sure what this stands for, but I found it interesting. So it's got like a lot of hashif defs and to just choose the heap ID, and I guess this would be really messy for the build system. So the overall problem is that we still use heap IDs, hard-coded heap IDs in our libraries, and we need to fix that. So there is a solution which is the new API that's been recently added to query the heaps on a platform, and along with the heap instances, you also get the heap type and the name of the heap. So one concern about this, which I brought up in XDC also, was that if you have so like in this example, you have three heap types which are of the same type. They're all CMA heaps, and if you see the blue users, these are the ones that use the CMA heaps. But each of these might want to use a different heap instance, and so just being aware of the heap type may not be sufficient. We also need to somehow get additional hints, which we can using the heap name. So this makes things a bit platform specific, but if you see all the applications, all the clients that are using the heaps, they're all very Qualcomm specific. So Wi-Fi display is a Qualcomm specific implementation, and camera libs are also proprietary post-processing libraries. So it's probably okay to have sort of Qualcomm specific code in some of these libraries, but the more generic guys like Gralloc and etc., they seem to not need it. But it's something that might come up later in the future. So so we also need to carry the heap name for these cases, and that's okay because it's anyway like platform specific user space. Does anyone have comments on that? All right. So I'll switch to the downstream kernel differences. So a lot of the code is to instantiate the heaps, parse it via DT, parse the DT and create the heaps. But yeah, you partially answered that we don't necessarily need a DT binding for ion. We can manage by other ways. The other thing is we have a few optimizations downstream that we're not able to upstream because of DMA mapping API abuse, DMA API abuse. So I'll quickly go through this. So in the upstream way, we allocate via something like via an approach like this, where if pages or compound pages are already in the page pool, we just it's like a cache, so we can just quickly this is the fast path, and if it's not available, if there's not enough space left in the page pool, then we allocate the pages using a GFP0, and we pass GFP0 so that the page is 0. And when we free the heaps, we zero the pages again. We add it all to the page pool, and that's how we make sure that the buffers are zeroed all the time. So we got a slightly more optimized path for allocation of system heaps. So what Qualcomm engineers realized was that on a heavily loaded platform where the page pool is already full and alloc pages is just spitting out 4K pages, the allocation time with this approach it really extends. It takes quite a bit, and the main problem is the alloc pages API that zeros these 4K pages individually. So what was done here was that we instead of relying on the buddy allocator to zero the pages, we just store them in a separate array and a separate SG list. The page pool guys go as it is, and then we map this entire the new pages into a contiguous address space and zero it in one whole swoop. So that gives us that really speeds up the ion allocations on loaded platforms. But one thing we need to do is to flush the cache out here, and we basically need to sync this SG list, and for that we do a DMA sync SG for device. But when we do it, we still don't have a valid attached device at the moment. So we use this fake, not fake, but this ion device to just flush the caches for us. So this is sort of DMA mapping API abuse, and there are other examples also where we sort of need to flush the caches to avoid artifacts, and this can happen before a DMA attachment happens. So yeah.
Yeah, but with the newer work, all of the extraneous DMA sync SGs have been removed because the goal should really just be to try and use the DMA buff sync APIs at the appropriate time.
So once this buffer is allocated and passed on to the user space, there would be certain pages that are still not. I mean, if the CPU accesses it, then we're in sort of trouble, right?
Yeah, that's the point though, is that the way it's supposed to work though is that you need to be calling these sync octals before you actually begin to access the buffer, just because that's how it syncs for the begin access to the cache that way. So.
Right, but I mean, if at this point, if this is available to user space and if we let user space access it, won't it lead to a security violation? Because we're not zeroing the buffers.
Well, zeroing is fine, but I'm talking about the cache sync.
Okay. But if the cache is not synced, and if there are still, some parts of the buffer that are still the invalid stuff, the older stuff.
Right, but then this is where you use the DMA of sync octals, because you commented that there aren't devices attached, but by definition, if there aren't devices attached, then syncing shouldn't actually matter because you should have already attached in order to actually have the syncing do anything, just because the point is that the sync is to synchronize between the CPU and an existing device, so it would have to be there would have to be some very strange edge case there where you need to sync where you haven't actually attached to the device though.
Okay. I was thinking of it more as a security violation thing. But yeah, probably have to think it through a bit more.
Yeah, no, you're right with the zero echo, but that should happen independent of the cache synchronization. So.
Okay. All right. So this is another difference that we've had, but it's in recent times has been resolved upstream. So it's the use of the custom caching IOCTLs that existed before and what we have now. So in the custom caching IOCTLs, we kind of call these custom IOCTLs to invalidate the caches, do the CPU access, and then go ahead and clean the caches. Flush the caches. So and this is basically the implementation of these IOCTLs inside the kernel. And what they do finally is to call these DMAC clean range, DMAC invalidate range API, which makes it ARM specific, and no one would accept this. So in order to fix this, the plan is to use the DMA buff sync IOCTLs, and inside the kernel, they look something like this. This basically tied with the begin and end CPU access DMA buff ops, and you iterate through every attachment and call a sync SG for CPU. So this sort of removes the platform, the underlying architecture dependencies. So a couple of points with that, with this new method is that there's no provision to flush a specific region in the buffer. We had that with the custom IOCTLs. So, we could pass the offset and the size. So here, we just have the DMA buff information that's contained within the DMA buff pointer. The other thing is that we can't call the sync IOCTL until there's at least one client attached to it. And the third, which I'm not sure if it's a legitimate concern or not, but we're sort of iterating through every possible attachment and calling sync SG for CPU, so might result in redundant flushes.
Yeah, to that point, I'd probably say this is something that can certainly be optimized. The initial first pass was to just get everything done and correct it. There's probably a chance to use an attribute somewhere like the DMA sync scape sync attribute.
Okay.
I talked a little bit this with Sumit at LPC, and I think my response is probably, yeah, you're right, there's probably unnecessarily work. If you come up with a proposal to do less syncing, then that would probably be fine. That also goes for your comment about being able to flush only partial buffer. That was, again, came up at LPC, some discussions with Sumit again. I think we're certainly open to a proposal for some sort of API extension to the DMA.sync.
Okay, cool. Yeah, so it's mostly good. Debug capabilities. So we internally, Qualcomm relies on the debugfs interface quite a bit. So there is one debugfs directory which specifies the heaps, and if you query into any particular heap instance, you sort of get a client name, you get the corresponding PID and the total size allocated. So, like for example, let's just look at this particular client. So it has a PID of 604. What we do now, we have another debugfs directory which specifies all the clients that exist on the platform, and we can find the same clients out here. So these are the corresponding clients, and if we cat into the clients, we would get the exact we would figure out what are the different heaps that this particular client uses, and what are the different allocations it's done. So this we can further use to sort of figure out which DMA buff FDs are currently in use, and we can it helps the teams inside to debug leaks and stuff. So these are going to go away. The client stuff has sort of gone, so we might want to bring some of this back without introducing clients. So we need some debug work to be done. Secure heaps I'll discuss as a separate topic. It's something that's really access control is really evolved with every SLC generation, and I didn't even mention this heap type in the beginning because I couldn't find it in like any 4.x kernel or even 3.18 or 3.10 kernels. So this is basically a carve-out heap which secures the carve-out region. So this is slave-side access control. Secure DMA is again slave-side access control, but with CMA heaps. So a slight improvement. Then system secure is a kind of a system heap, but it works with platforms that support hypervisor. You can achieve access control on any master by removing the stage 2 mappings of the buffer that you want to protect. And so calling the hypervisor for every individual page can be expensive, so that leads to performance slowdowns. So we also have a method to allocate a contiguous CMA heap, which implements master-side access control by a single hypervisor call. So the challenge with the secure heaps is that the semantics vary. There's one flag for this guy, and we sort of need to pass a hint to the allocation IOCTL to specify what are the masters in the pipeline that are going to use this buffer. So this internally translates to a VMID, which the hypervisor then figures out, okay, I have to erase the page table mappings from these stage 2 context bands. So there are some additional IOCTLs to optimize secure heap allocation. So there's a prefetch and a train IOCTL that's not upstream yet, but we would require it if we want the performance numbers that we do. So yeah, I think secure heaps is still something that we have to figure out, and I'm sure every SOC vendor would have their own thing. So it would be nice if we can sort of gather the requirements and come out with a more standard API. So this is something I just added because it sounds cool. So virtualized platforms, especially on ARM SoCs, is relatively new, and most of the early implementations start by carving out memory. So this sort of introduces the need of carve out memory again. It's mostly because the hypervisor code is still in its nascent stages, and it's not very good with dealing with IMNUs. So one issue that this brings out is that you might have an MSM8998 platform which uses the system heap for all regular use cases, but when it's in a hypervised sort of setup, it would need to use the carve-out heaps now. So using hard-coded heap in IDs would definitely be a problem here, because we would need to add another set of checks. But if we add the query mechanism out here, and if we make the user space slightly more clever to first try the system heap and then fall back to carve out, it will make life much easier. So this is one thing the teams inside who are looking for. So they basically want a carve-out heap type, which also has a page pool sort of layer, as with system heaps.
Doesn't that kind of defeat the point? Because the point of a carve-out is that you don't have the penalties from allocating from the system heap.
Yeah, but so this page pool is, it's never going to go via the buddy allocator, but just like an additional layer of caching.
Yeah, but why? The carve-out heap currently is just a bitmap allocator. It's very fast, so I don't understand exactly what a page pool for a carve-out heap would even get you.
I'm also not entirely sure, but might have. I don't know. Yeah, it sounded a bit vague to me also. So again, this is like very downstream code, and based on the hypervisor that you're using, you might need tweaks in how you allocate things. So there are more messy, like hash if this hypervisor on this system, then do this, otherwise do that. So, but yeah, these should ideally go away as the stack matures. This is something that's probably we'll deal with in the future, where we would need to implement secure use cases, but also have the hypervisor on. So this is something we're seeing internally, that there's going to be a conflict between hypervisor and master side access control usage. Yeah, so that's the end of it. I'm just going to summarize the problems. So we can remove kernel clients mostly. In some places we have to still figure out secure heaps. Maybe we can allocate the secure scratch buffers in Userspace and pass them down. But we could ideally avoid using kernel clients.
The real thing about the kernel clients is that using IAM is essentially just a wrapper around a couple of allocation mechanisms, so there's not a whole lot. It's a bit redundant to try and have it in the kernel. I'd probably say is that if you want the same allocation mechanism and stuff, should probably be refactored to try and do things that way. Especially, if are the scratch buffers actually being shared back up to Userspace, or?
They're not being shared by the Userspace. It's totally internal to the hardware encoder decoder.
Yeah, that's an even better argument not to use IAM at all, just because it defeats the point to have the DNA off there. So.
Right, but we still don't have a way to allocate a secure buffer in kernel. So I guess once we figure that out, it should be okay. So, so hardcoded heap IDs looks like a thing of the past. It should go away, but it would still be a huge headache to support the existing Android Userspace stack. So it's nice for the future, but it would require a lot more management to keep backward compatibility inside for Android Userspace that exists downstream. Cache maintenance mostly looks good with the DMF of sync IOCTL, and there are a couple of issues, but we're aware of that. The ion debugging requires some more work. The secure heaps, at the moment, they leak out implementation details to Userspace. That's something we also have to figure out, and we should try to keep things virtualization friendly, because that's the future apparently. So that's it. Thanks. Any questions?
I know often getting some of the details is hard to make public and things like that, but I feel like one of the difficulties we've always had with ION is the specifics of what people want as sort of an implementation, and very rarely do we get the whys. And so that's that aspect that I was kind of chuckling about with the virtualization, because it's like, if we really understood, what it was, then that helps a lot trying to abstract an interface for user space. So yeah, so if there's any way to help extract those sort of whys out,
Okay.
that would be great.
Okay. Anything else?
Also, just kudos for going through this. There's not a lot of funders who have done much feedback for ION, so this is really awesome to get. So.
All right. Thank you, guys.